Hi everyone, hope you're all doing well. In the last scientific critical thinking video, we talked about the difference between claims and evidence. And that when someone makes a claim and they want that claim to be taken seriously, evidence needs to be provided for that claim. So let's look at a particular claim known as Archimedes Principle, which states that when an object is submerged in a fluid, the buoyant force, that is, the force of the fluid pushing up on the object, will be equal to the weight of the fluid displaced. So that's our claim, and we're going to do an experiment to try to provide evidence for this claim. We're also going to use this experiment to test a different, more general aspect of forces and Newton's laws in an interesting way. So even if you're already convinced that Archimedes' principle is accurate, I'd encourage you to stick around or jump ahead in the video to see how this experiment can be used to test Newton's third law. But before we get into the experiment, let's dive a little bit more into the claim and how we're going to test it. We can describe Archimedes' principle with this equation, that the buoyant force is equal to the density of the fluid times the volume of the fluid that was displaced times little g, the gravitational acceleration on the Earth. This is 9.8 meters per second squared. So basically, when an object is submerged in the fluid, that object's volume will push some of the fluid out of the way. And that's going to be our volume displaced. And then the density of the fluid is that fluid's mass per unit volume. So the fluid density times the volume displaced would give us the mass of the fluid displaced. And multiplying that by little g gives us the weight of the fluid displaced, the gravitational force that would act on that fluid that was pushed out of the way by the object. And according to Archimedes' principle, this should match how much the fluid pushes up on the object, the buoyant force. So how are we actually going to test this claim? Remember, any evidence should be consistent with the claim. If it's evidence for that claim, it should be consistent with the claim, and data that we would not expect to match up if the claim were false. So what we're going to look at in this case is we're going to set up an experiment where we can separately measure what is the buoyant force acting on the object and what is the weight of the fluid displaced. If the claim is true, those should match up. If the claim is not true, then there shouldn't be any reason that those two values would match up with each other. And we're going to do this by hanging a mass from a string and submerging it into a fluid. And we're going to separately measure the buoyant force based on how the tension in this string is changing, and measure the weight of the fluid displaced based on how this water level is changing. So let's look at this in a little bit more detail. Suppose I have this object hanging in air where there's no acceleration. It's just not moving, hanging in air. Well, in this case, there are two forces that are going to be acting on this object. There's going to be the tension force pulling up, and I'm going to highlight this as this is the tension force when it's just in the air, and the force of gravity pulling down. According to Newton's first law, an object will keep its exact same motion, so right now it's not moving and continuing to not move, unless there's some net force. So in this case, it's not accelerating in any way, so the net force has to be zero, which means that these two forces, the force of tension pulling up and the force of gravity pulling down, should balance each other. But now let's say I take this object and I either fully or partially submerge it into a fluid. If I have this hanging mass in a fluid, and again, it's not accelerating, so the forces on it have to be balanced. In this case, our forces are, there's still the force of gravity pulling down, same force of gravity, but now we've got both the force of tension pulling up from that string, and there's a buoyant force that's pointing upwards. And if this system is not accelerating, those forces should be balanced, so we can say that the force of tension when the object is submerged plus the buoyant force is equal to the force of gravity. But that force of gravity, we already said that force of gravity should be equal to the tension force when the object is in the air. So if I do a quick rearrangement, we can show that, again, in this model, the buoyant force should match how that tension force changes when I go from having the object hanging in air to having this object submerged in the fluid. Basically, when the object is submerged in the fluid, that buoyant force is counteracting some of the gravitational force that was acting on this object. Not generally all of it, but that buoyant force is counteracting some of the gravitational force. Which means the tension, when the object is submerged, doesn't have to be as high. So if we can measure how this tension force changes when I submerge the object, that's going to give us a direct way of measuring the buoyant force. But we also need to be able to measure what is the weight of the fluid being displaced. So for that, when we submerge the fluid in this graduated cylinder, we're going to be able to measure what is the original water level, or the original fluid level in this graduated cylinder. As we submerge the object in the fluid, that fluid level is going to change. As I submerge the object, that's going to displace some fluid, and that's going to cause that fluid level to rise. If we can measure how much that fluid level has changed, that's going to match the volume displaced. And depending on what fluid you're using, for the first experiment, we're just going to use water. We know the density of water is 1 gram per milliliter, or 0.001 kilograms per milliliter. If I know that density of the fluid, and I've measured the volume displaced, and I know g on the Earth is just 9.8 meters per second squared, we have a way of calculating and measuring what is the weight of the fluid that was displaced. Okay. So this is the experiment that we're going to do. Again, our claim is Archimedes' Principle, that the buoyant force is equal to the weight of the fluid displaced. We have a way of measuring the buoyant force by measuring how the tension in that string changes when we're in air and when the object is submerged. And if I can measure the displacement, how much the fluid level changes, then we can figure out the volume displaced, and if I know the density of water, we're going to be able to calculate the weight of the water displaced. So let's get set up and actually do the experiment. So let's have a bit of a closer look at our experimental setup. I've got a force sensor up here, and this is what we're going to be hanging our mass from so we can constantly measure what the tension in that string is. I've zeroed the force sensor, so when I pull on this a little bit, we start getting a positive value for that force, so we're going to be able to measure what is the tension in that string when the object is just in the air and when the object is submerged. I've also got my graduated cylinder, and we're going to be able to read the water level readings to figure out what is the volume of water being displaced. I got a second camera set up so we can have a closer look at those particular measurements. And one other thing that we're also going to be doing is measuring what's happening to the apparent weight of this beaker. So as the object gets submerged in this fluid, what's happening to the apparent weight of the beaker? So I'm going to zero this now. So we're just getting how is that apparent weight of the beaker, the normal force that's pushing up on the beaker, how is that going to be changing? So let's add some water to this thing. We don't need any particular amount, but say around half full. So let's add some water to this. Okay. Maybe get around, I was trying to aim for 150 for the fluid level. So let's take a look at this. Getting that water level, I tried to get that, that worked pretty well. I got that around 150 for the water level. And notice that the mass in kilograms is around 0.15, just a little bit shy of that. So again, that matches up with this density of water value that is 0.001 kilograms per milliliter. I'm still going to zero that one. So again, when we start putting the object into this beaker, we're going to be able to measure how is the normal force acting on the graduated cylinder going to change. We also, so we can label that as our original fluid level, 150 milliliters. Happy with how that one worked out. Yeah, close enough. And let's get the tension in this string when this is just hanging in air. So I have this object just hanging from that force sensor in air. Does jump around a little bit. Maybe I'll make sure this is hopefully not spinning quite as much. Let that motion kind of settle out a little bit. But it looks like we're getting a force of around 1.08 newtons for our original tension in air. Okay, so let's put these pieces together. And hopefully this is nicely aligned so it's not hitting the sides or anything. The cylinder in there is not hitting the sides. And again, in our original start, I've zeroed this so there's no reading from the scale. Our original water level is at 150 milliliters. Let me rotate that a little bit so you can see that a little bit better. And before I've actually started submerging this object into the fluid, the force acting on that is around 1.08 newtons. So let's start by trying to submerge this object about a quarter of the way in. This doesn't have to be exact. If I'm a little bit off, that's okay. I'm still going to be taking my measurements directly from the sensor, the changing water level, and the scale reading. So let's give this a start, and I'm going to lower this into the water. So again, we want it about a quarter submerged. Could be a little more, could be a little less. We'll stop that there. Okay. So let's see what we're getting in terms of readings. So our force sensor, again, it jumps around a little bit, but not too much. Our force sensor seems to be around 0.988, 0.988 newtons. Our water level, if we look at that one closely, that looks really close to 160 milliliters. So let's label that as 160 milliliters for the volume. Well, if the original volume was 150 milliliters and our new volume is 160 milliliters, well, that volume that was displaced, that water level changed by 10 milliliters. And let's also look at our scale reading, just so we get this, just in case this tries to reset on me. So that scale reading is 0.0094 kilograms. So that is our new scale reading. 0.0094 kilograms. Okay. Now, let's identify a couple of things about this setup. So we said that the buoyant force should be the difference between the tension when it's in the air and the tension when it's submerged. Our tension in the air was 1.08 newtons, minus our tension submerged, 0.988. I got 0.092 newtons for that difference. Okay. If we try to identify what is the weight of the fluid being displaced, well, we've got 10 milliliters, and it's 0.001 kilograms per milliliter. So if I multiply those two together, that gives us 0.01 kilograms of water being displaced. 0.01 kilograms of water. And to get the weight of that, we have our density of the fluid, 0.001 kilograms per milliliter, 10 milliliters displaced, times 9.8, I get 0.098 newtons for the weight of the fluid being displaced. And last one on here, let's look at this change in the normal force. Well, if our scale reading went up by 0.0094 kilograms, to get the effective change in the normal force, we have to multiply this one by 9.8. So 0.0094 times 9.8, I got 0.092. Okay. So again, our original claim is that the buoyant force should be equal to the weight of the fluid displaced, And it looks like those are matching up. I'll throw a percent difference on after calculating that, but looks like maybe 6 or 7% off. But also, strangely enough, this also seems to match the change in the normal force acting on this graduated cylinder. Well, let's try another trial. Let's lower this a little bit further in. Let's see if we can get it about half submerged. Somewhere around there. Okay, so this is around half submerged. Our new tension force looks like it's 0.893, maybe? Okay, jumps around a little bit. And if we take the difference between the original tension and this new tension when it's submerged, I get 0.187 newtons. Well, let's look at the water level. And the water level looks like it's pretty close to 170. So if our original water level was 150, that was a displacement of 20 milliliters of water. And to get the weight of this fluid displaced, we do 20 milliliters times 0.001 kilograms per milliliter times little g, times the 9.8. So if I multiply those together, I get 0.196 newtons. And let's also look at our scale reading. So our scale is now reading the change in the apparent weight of this cup is 0.0190 kilograms. And to convert that into the change in the normal force, we multiply that by 9.8. And I get 0.186. Now, as we're going through these, it is important to note that there is a limitation on how accurately I can measure these water levels. I wouldn't trust that to closer than a gram, being closer off than a gram. So that could be up to 10% off on this one, maybe 5 or so percent off on this one. We are going to get some measurement error in these volumes displaced, but let's try another example, because we still seem to be getting that the buoyant force is pretty close to the weight of the fluid displaced, and also very close to the change in the normal force acting on this. Let's try another case. So I'm going to lower this to about 3/4 submerged. And I want to make sure it's not touching the sides or anything. So this new case is around 3/4 submerged. Our new tension force is 0.806, let's call that. And if I take the difference between the original tension, 1.08 minus 0.806, I get 0.274. And let's look at these water levels. So if I look at that water level, looks like it's a little bit under 180. Let's call it 179. So going from 150 to 179, that would be 29 milliliters for the volume displaced. And our new scale reading is 0.0279 kilograms. Okay. So let's do the same kind of calculations that we were doing before. For the weight of the fluid displaced, it's the volume, 29 milliliters, times the density, 0.001 kilograms per milliliter, times little g, 9.8, and I got 0.284 newtons. For the change in this normal force acting on the beaker, it's the 0.0279, the new scale reading, times 9.8. So that's 0.273 newtons. Once again, buoyant force weight of the fluid displaced, and the change in the normal force, all in pretty good agreement with each other. And again, I'll put the percent errors, the percent differences between the buoyant force and the weight of the fluid displaced in afterwards. Well, let's try one more. Let's try fully submerged. So now I'm going to have this thing fully submerged in the water. Okay, so I'm having it just below the surface. And let's take these scale readings. So this is full submerge. Our new force of tension is 0.702, looks like. So taking the difference with the original tension, I got 0.378. These should both be in newtons. In terms of some of these other readings, the volume displaced. Again, looks like we're just below 190, so let's call it 189. So if it's going from 150 to 189, that is 39 milliliters displaced. Taking that volume displaced times the density times little g, I get 0.382 newtons. And if we look at our scale reading is now 0.0386 kilograms. And if we multiply that by 9.8, I get 0.378 newtons. Once again, we get a very good agreement between, this one actually seems the best one yet, a very good agreement between the buoyant force, the weight of the fluid displaced, and the change in the normal force. So those all seem to match up with each other. Again, the main ones that we were looking at for Archimedes' principle is that the buoyant force is equal to the weight of the fluid displaced. And it looks like in all of these cases, those numbers have some pretty good matching. But we want to test Archimedes' principle under as many different circumstances as we can manage. So we just barely submerged this thing. What if I lowered it further into the fluid? According to Archimedes' principle, nothing should really change because we haven't changed. If I just move this lower in the fluid, I haven't really changed anything about what is the volume being displaced. So according to Archimedes' principle, the depth, once it's fully submerged, the depth in the fluid shouldn't matter. Well, that's a claim that we can test. So let me try moving this further into the water. I'm not going to have it touch the bottom, because if it touches the bottom, then instead of just the buoyant force and the tension force pulling up, there would also be a normal force pulling up. So we don't want any other forces acting on this. And, well, if we look at this force sensor reading, nothing has really changed. It's still hovering around 0.702. If we look at the water level, well, that's still just under 190, so still the same 39 milliliter displacement. Again, it's not touching the bottom. And our scale reading is changed by, maybe a tenth of a gram. Sorry, maybe around 1 gram. So again, not a very significant change in any of these circumstances. So based on that, we can accurately say that, well, if we change the depth of this object, it still satisfies Archimedes' principle. Once the object is fully submerged, how deep it is in the fluid doesn't actually matter. So this is data, again, that seems to support Archimedes' principle. We seem to have this match between the buoyant force and the weight of the fluid displaced. But why is this change in the normal force also matching up? Well, this is kind of an interesting test of Newton's third law. So if you remember, Newton's third law is the action-reaction principle. It basically says if two objects are in contact with each other, and object 1 exerts a force on object 2, object 2 will exert exactly the opposite force on object 1. Okay. Those forces are vectors. They have a magnitude and direction, and when object 1 pushes on object 2 pushes back on object 1 with exactly the same amount of force, but in the opposite direction. So that means if we look at what's happening with the water in here, the water is pushing up on the object with that strength of the buoyant force that we've measured. The water is pushing up on the object. Well, if the water is pushing up on the object, that also necessarily means that the object is pushing down on the water with that exact same amount of force. Equal and opposite forces. When object 1 pushes on object 2 pushes back on object 1. When the water pushes up on this object, that means the object is also pushing down on the water. And if it's pushing down on the water, that will change this scale reading by exactly the right amount to match that buoyant force. This is a consequence of Newton's third law. And it's one that we don't think about too often. Like when you go swimming, you think of, oh, the water is pushing up on me, stopping me from sinking. You don't really think about the fact that you are pushing down on the water with exactly the same amount of force that the water is pushing up on you. But Newton's third law applies to any forces between any two objects. If object 1 is pushing on object 2 is pushing back on 1 with an exactly opposite force. But let's see if there are any other ways that we can test out this system. So let's try the same kind of experiment, but instead of using water, which had a density of 1 gram per milliliter, I've got some high purity isopropyl alcohol, which has a density of 0.786 grams per milliliter. So let's see if this still has this matchup between the buoyant force and the weight of the fluid being displaced. So the original tension, looks like the calibration might have changed slightly. So let's call this 1.08. Let's still call it 1.08. Seems to be still jumping around there. And let's measure out some isopropyl alcohol. So I'll put this into here. Okay. Now it's not going to be as exact as the last one, but we'll still make it work. So let's seal that up. And if we put this on the scale right now, we can measure that original fluid level. Bottom of that is around 153 for the bottom of that part. So let's label that as our original fluid level. So 153 milliliters. And let's just do the half submerged and then the fully submerged cases. So we'll do 2 cases for this. So I'm going to move this down. Actually, we need to make sure that this is zeroed first. So again, our scale is 0 to begin with. And then let's give this a start. So here we go. We want around half submerged. Lock that off. And now, with this being half submerged, our force of tension is around 940. And if we take the difference from the original tension, that gives us a buoyant force of 0.14, which notice is significantly less than what we had last time this was half submerged. Again, it could be off, but let's check the other numbers. So for the volume displaced, the current water level looks like it's right around 170. 172 or 173? Let's call it 172 and a half. So if we're going from 153 to 172 and a half, that should be 19.5. Let me just make sure that I'm not messing that up. Yeah, 19.5 milliliters for the volume displaced. And our scale reading is 0.0145. 0.0145. Okay, so for the weight of the fluid displaced, we need this volume displaced, the 19.5 milliliters, times our density of 0.000786, and then multiply that by little g, 9.8, and I get 1.50 newtons. If I take the change in the scale reading, this was in kilograms. And to get the change in the normal force acting on the beaker, we have to multiply that by 9.8. So 0.0145 times 9.8, we get 0.142 newtons. Again, this buoyant force was in newtons. Let's make sure we include units on everything. Okay. So this trial, once again, we get buoyant force, weight of fluid displaced, and the change in the scale reading, because if the fluid is pushing up on the object, that means it's also pushing down on the scale. All of those seem to be matching up with each other to, pretty decent accuracy. So let's switch this up to fully submerged. Let's move this down so it's now fully submerged in the alcohol. So this is full submerged. Our new tension force is 0.78, it's jumping around a little bit. Let's say 0.784 newtons. So if we take the difference from the original tension, that gives us 0.296 newtons. Our new volume... Our new volume looks like it's right at 192 milliliters. So if we started at 153 and we're now at 192, that should be a difference of 39 milliliters. And if we take that 39 milliliters, multiply it by this density, the 0.000786, and then multiply that by 9.8, I get 0.300 newtons for the buoyant force. And as for our scale reading is 0.030, it's jumping around a bit, but let's say 0.0305. And if we multiply that by 9.8, 0.0305 times 9.8, we get 0.299 newtons. So again, we've changed what fluid we're using. It has a different density, a lower density than the water, and we still seem to be satisfying all of these aspects of Archimedes' principle. The buoyant force matches the weight of the fluid displaced, and if that buoyant force is the fluid pushing up on the object, that means the object is pushing down on the fluid, and that makes the scale reading change by an amount that matches. But in all these cases, this object, this cylindrical metal object, it's the same object each time. So maybe there's something special about this object, or maybe the fact that it has a flat bottom, maybe that has an effect on this buoyant force. So let's do one more test of this. So in this last experiment, we're going to change things up with the object that we're using. In the previous experiments, we've used an aluminum cylinder, which had a flat bottom, and maybe that changes how the buoyancy force works. Here we have a steel sphere, so it's a rounded bottom. It's got a higher density, so it's a different mass, a different volume. And let's see what happens in this case. Now, unfortunately, this sphere is too large to fit in the graduated cylinder, so what we can do to figure out the volume instead is just measure the volume of this sphere. So if I take my calipers and measure what is the diameter of this sphere, I'm getting 38.1 millimeters. So if that is 38.1 millimeters for the diameter, then we can convert that to 3.81 centimeters, divide that by 2 to get the radius, and then to find the volume of a sphere, it's 4/3 times pi times the radius cubed. So we can cube that, multiply by pi, multiply by 4, divide by 3. I got right around 29 cubic centimeters. And a cubic centimeter is the same as a milliliter. So we can say that the volume of water that's displaced when we fully submerge this is going to be 29 milliliters. Okay, so this is going to be the full submerge for the steel sphere. Now, in terms of the other values, we don't need the fluid level. We're just back to ordinary water, so density of 0.001 kilograms per milliliter. And our original tension is right around 2.2, looks like 2.22 for the original tension. And let's submerge this in the object. Again, we've zeroed this. Let me re-zero that to make sure we've got our scale reading zeroed as well. And let's submerge this in the fluid. So again, we want this fully submerged, but not touching the bottom. So, yep, that is fully submerged, not touching the bottom. And let's see some of these values. So our tension reading is around 1.93, it's jumping around a bit. Let's call it 1.934. Just jumping around a little bit. And if we measure the difference from the original tension, I get a buoyant force of 0.286 newtons. If we take our volume displaced, which was just the volume of the steel sphere, so 29 times 0.001 times 9.8 to get the weight of the fluid displaced, that gives me 0.284 newtons. Very good agreement. Our new scale reading is 0.0288 kilograms. And if I take that value, 0.0288, multiply by 9.8, I get 0.282 newtons. Once again, even though we have a different shaped object, a sphere instead of a cylinder, we have a different kind of material, iron instead of aluminum, we still get the buoyant force, the weight of the fluid displaced, and this change in the normal force. Once again, if the buoyant force is the fluid pushing up on the object is pushing down on the fluid an equal amount. We get all of those matching. So with all of this data that we've taken, we seem to have gotten a lot of evidence, a lot of data that supports Archimedes' principle, supports this idea that the buoyant force is equal to the weight of the fluid displaced. It worked for the cylinder in ordinary water. When we compare those, we get pretty good agreements across the board. It worked when we changed our fluid to isopropyl alcohol instead. We still got that match of the buoyant force and the weight of the fluid displaced. Or when we used the steel sphere. All of this is data that is consistent with the claim and would be very, very unlikely for us to have happened upon just by accident. If Archimedes' principle was not true, we wouldn't expect the numbers to match up this accurately, this consistently, under this many different cases. So this is what it looks like when you have a claim and now you're providing evidence for that claim. So that's where we'll leave this one today. As always, thank you for the view. If you have questions or comments or ideas for other kinds of experiments, throw those into the comments. I really appreciate that, and have a good rest of your day.